Thanks, Shaoli. Thanks, Vinay, for organizing this on such short notice. I'm Panos. I'm from the Econometrics and Statistics group at the Booth School of Business at the University of Chicago. I'm excited to present this work. This is still ongoing work. It's joined with Jacob Bean, also the University of Chicago. And I'm excited because this work combines things that I like in research, which is randomization methods in general for inference, and also a cool applied project. So without further ado, let me present a slide that even my kids can get excited about, which is kind of try to motivate that question of estimating periodicity, right? And one of the interesting examples of that in research is whether biological extinctions are periodic or not. And there have been some very nice papers on the 80s, intriguing papers that put forward that idea that the biological extinctions are periodic and they have a 26 million year cycle. That was contested very early, of course, like a few years later, actually by Stigler and Wagner here at the University of Chicago. They kind of showed that there might be some problems with this discovery, but this discovery, it still lives on, and there's still debates. And intriguingly, it's connected to the hypothesis of whether there are two suns in our solar system. And the theory goes that there might be a second sun somewhere, and periodically it ejects stuff from the Kuiper belt towards Earth. So I understand it's still an ongoing debate, but the bottom line is it's an important problem, right? Since it affects our long-term survival. So hopefully that establishes the motivation here, our very, very long-term survival. Now, more seriously, of course, the estimation of periodicities is an important problem in science, and we're going to see an example from astronomy today, but we have paleontology, biology, climate science. All of them have problems of estimating periodicity. And the problem might appear to be simple. You might say, okay, let me take a periodic model, let estimate it, and this will be kind of invoke some standard theory, but actually it's deceptively simple. Standard methods typically require assumption of observation times being some structure on the observation times. That is, that they have equal spacings or their i.i.d. And they also need assumptions or conditions that guarantee that the estimators that are being used, like the periodogram peaks that I'm going to introduce later, that they do have nice statistical properties. They're consistent, they're asymptotically normal, and so on and so forth. Now, the argument in this paper, and this is how we start, is that these conditions are highly unrealistic in this setting. First, the observation times do exhibit very strong patterns. They have their own periodicities, and that's a problem for inference. And second, the estimators are applied on likelihood models that are highly irregular. And the fact that we kind of work with irregular likelihoods, with irregular models, means that the estimators can substantially deviate from normality. So I'll try to make that point with a little bit of theory, and also with some real examples as well. So we do have these problems, and it's not clear how inference proceeds, because of the standard methods, including the asymptotic frequentist methods or even Bayesian methods, can break down in this setting and in a really bad way. The motivation for this talk and for this paper is the analysis of radial velocity data for exoplanet detection. This is obviously an important, I want to preach to the choir, it's obviously an important problem in astrophysics and astronomy. In 2019, it was awarded the Nobel Prize for the discovery of 51 PEG-SCP. And even more recently, there's been some astonishing discoveries in our immediate neighborhood, which is astonishing because it suggests that the exoplanets are maybe ubiquitous in the universe, which is an exciting discovery. Now, despite these successes, however, the underlying statistics, the underlying statistical methods, they do need improvement. And depending on who you talk to, it might even need a complete overhaul. And the problem is that false discoveries are not uncommon. So what happens in practice is usually some sort of standard method plus lots of heuristics. So what we're trying to contribute here is just put some principles behind those heuristics that people use to kind of test and check those detections, those discoveries. Okay, so not to be too ambitious, I want to make 4 main points today. One will be about the background, kind of set up some notation and present the challenges of the problem. The second will be to describe our main method, that we propose for estimation of periodicity. Three will be the applications, and I'm going to give particular examples, illustrate how our method works with four different examples, four real examples of exoplanet detection. Two of them are confirmed, two of them are not confirmed, and for the unconfirmed ones, we're going to be a little bit negative. I'm going to show evidence that some discoveries don't really hold up, but we also will try to be constructive in the sense that we're going to propose also observation designs that can help us deal with those negative results. Okay, going forward, and hopefully help with future discoveries as well. Now, if there's time, I can talk about other things, especially to statisticians who might find it interesting, especially about how this method that I propose today relates to what it implies for statistical inference at large. Because I'm going to argue that our method is a third way of doing statistical inference, which is distinct from asymptotic frequentist, and also distinct from Bayesian methods as well. And I'm going to make strong arguments against both of these standard approaches, and clearly I'll try to convince you as much as possible about the future and the benefits of that third way. Okay, but let me go through the main material first, and then we can take this more scenic route, this more philosophical route. Okay, a little bit of background right now. Exoplanet detection, I'm just going to repeat what my collaborator told me about that. There's obviously a lot of science behind it that I don't understand, so please stop me if I'm embarrassing myself. So what I understand is stars are round and shiny, and if there's an exoplanet moving around it, there's a gravitational seesaw that's happening, and that affects the light that's coming from the planet, like the Doppler effect. On Earth, we're doing some spectroscopy analysis, and we kind of see that as variations, oscillations in the spectrum from the star. And from that, we back out the velocity of the star with respect to Earth, the so-called radial velocity. And so essentially, we're looking for the fingerprint of the exoplanet as oscillations, as periodicities in this data of the radial velocity data from the star. That's basically what's happening here. Now, reality is more complex. There are more phenomena that are can kind of leave the same fingerprint on the data, the same kind of oscillations, the similar oscillations, and so it's an interesting statistical.
Panos?
Yeah.
So I mean, I understand that you're using exoplanets as a specific case, use case. But not, I don't know if is your methods specifically targeted towards the radial velocities, or is it just that it's just happened to be a convenient variable?
It happens to be convenient. There's nothing special about exoplanet detection that we needed for the method to work. It just happens that my collaborator kind of works in exoplanet detection. So we were able to find very good examples, kind of set up our analysis in a way that's convenient, kind of shows all the intricacies of the problem, but there's nothing special about the problem that we need. Yeah. So as I said, there are interesting statistical problems about disentangling the effects from the exoplanets and other phenomena that might leave leave the same fingerprints, like rotation of the star or the magnetic cycle of the star, things like that. I'm going to ignore those interesting problems. I'm going to focus mostly on just estimating periodicity from a signal. That's basically my setup. And so for this problem, there are two steps. Basically, one step is detection of any kind of periodicity. And then the second step, if we have detected periodicity, then actually go ahead and estimate it. Okay. Now, the detection problem is actually quite robust. We know a lot about it. It's a well-studied problem. So does not pose any challenges to us. But I will start from that because it will help me set up some notation, set up some terminology, and then it will help me also kind of illustrate the intricacies of the problem, so that when we get to the real problem, which is estimation, we will be kind of we'll have all the tools that are and the terminology that is necessary. So a little bit of notation. It's very basic. So we have observation times. This T of n is the observation vector. Y of n are the radial velocity measurements. So observation times are Earth days. Radial velocity measurements is just basically velocity measurements. The differences between the observation times is what I call spacings between the observation times. And we can think, we can conceptualize a distribution for these observation times, right? We'd like these observation times to be completely random because intuitively this would lead to best inference. However, the problem here is that this can be far from being random, or at least there are very strong deterministic patterns in that distribution, or like biases. For instance, the observation times usually have to happen during the summer. They have to happen during the night, and they also have to happen in a specific window where the position of the star is favorable. So there are all these physical constraints that are kind of imprinted into the observation design, and this very fact is going to imprint some signals, some nuisance signals in our actual data. So we have to be really careful about disentangling those spurious signals from the real signals. And actually, this fact has created a lot of problems for inference, which I'm going to describe later. Now, I still call this observation design because I want to emphasize that there is some kind of control that we have over these observation times. And even though, just talking to the experts, even though it's not a practice right now, we don't really randomize observation times. We don't really think about what's the best way to design when we take the times for when we take the observations. I think it will be a good practice. And actually, towards the end of the talk, I'm going to show some simulations, some examples of the benefits that you get from simply just randomizing these observation times a little bit. Okay, can go a long way. All right, let me go back though to the. So this is our setup. Our question is, how can we detect periodicities in this very simple setup? And let's go back to this detection of periodicity problem. Okay. The fundamental object here is the so-called periodogram. It was invented even a century ago by Schuster, and is essentially you take the Fourier analysis of your data and you look into the Fourier coefficients. That's basically it. And then the power this is the power at every frequency or every period, and that's your periodogram as a function of the frequency or equivalently of the period. But this is true for equal spacings. For unequal spacings, it was extended by Loeb and Scraggle in their seminal work, and this is what I'm going to present right now, the Loeb-Scraggle, the so-called Loeb-Scraggle periodogram. And this is useful to us because it has a nice least squares, equivalent least squares interpretation. So that makes it even more intuitive to statisticians. So here's how we can describe this periodogram. So suppose that the data satisfy this model. The radial velocity has a regression component here that has these periodic components, the cosine and the sine terms. These psi stars are the regression coefficients for these periodic components. And then theta star is my unknown parameter. Okay, so I can write this as a periodic component here, yp, and then theta star is a period again, and the psi star are these regression coefficients, and then plus an error component. I will use the term nuisance parameters for this psi star because we're going to focus on estimation of periodicity, but I should clarify that for detection of periodicity, these are not nuisance parameters because detection of periodicity is basically the null hypothesis that these two coefficients are zero. Okay, so with that model, the periodogram is essentially comparing a model where we include these periodic terms at the specific parameter value, period value theta, with a model where we just don't include this, with a baseline model where we don't use these periodic components. So this is the definition, just one definition. I'm using the generalized Loeb-Scraggle definition, but there are many different variants of that, but more or less all of them are equivalent. So the periodogram is the Loeb-Scraggle periodogram is a function of the period where, as I said before, we're comparing the baseline fit from an empty for the empty model, like the basic model with just the with one intercept, and then the model where we include the periodic components. Okay, and then this gives me a value, and that value you can think of it as it's similar to the likelihood. Okay, because so the larger this value is, the higher the likelihood value for that particular value of the period. Okay, and L here is a squared loss. Equivalently is the normal likelihood. This psi star that I'm using is essentially the restricted MLE, the given, assuming that the actual period is equal to theta, and then L0n is this baseline. This is the baseline fit, the baseline loss. As statisticians, like we can look at that and we can interpret this in many ways. This looks like an F statistic. It's not exactly an F statistic, but it definitely looks like an F statistic because we're comparing the residual sum of squares. It looks like a likelihood ratio test also, because we're just having this ratio. You can think of it as a ratio between likelihoods. So there are many ways we can look at that. And actually, that's exactly how people are using it in order to do statistics with it, right? Because you can connect it to chi-square distributions, and then you can assess significance based on these periodogram values. And here's how this period.
I'm sorry,
Yeah.
may I ask a
Sure.
question?
Definitely,
can you
yes.
go back to page 9?
Yeah.
Yeah, so I missed the beginning of your talk, so I may have missed something. But in here, your model for yi, so it seems like you're only allowing for one frequency.
Yes,
only
yes.
one theta is in there. So you
Yep.
are not allowing for multiple frequencies.
I'm not allowing for multi-period models. Yes,
Okay.
I'll do only one period. Yeah.
Okay, thank you.
Yep. So this is how a periodogram looks like. So on the x-axis, I have basically I have discretized the period parameter space, and then the y-axis I have the periodogram values. And so you can think of these values here as I said before, like the likelihood for that period. And you can see that sometimes we see some clear peaks. Some other times we see basically just some areas of like very low likelihood values. And then the idea is when we try to detect periodicity, the main idea is to look at the peak of that periodogram and then argue, is that peak statistically significant? Okay, that's basically the majority of the methods that are being used right now. The first who actually derived this kind of a kind of test like that was, of course, Fisher, and it was later refined in terms of power by other researchers. Fisher used a kind of different statistic. It was the periodogram peak divided by the average periodogram values, and he derived the exact distribution. Kind of looks like a gamma, but it isn't exactly a gamma. But this is as I said, is a well-studied problem. In astronomy, you might hear the term false alarm probability. Like you kind of assume you derive some approximations using extreme value theory. You can say that this is the 1% level, and if it exceeds that, then we know that the signal is periodic. Okay, so as I said, very well studied, robust. So there's nothing really that it poses no real challenges for us. But the question is, of course, after we've done that, right, and after we have detected periodicity, how do we really use that periodogram peak to do inference for the true period? Okay, so this is where the problems start for us. And a common mistake, surprisingly common mistake in practice, is to interpret this detection of periodicity meaning that as if the theta star, the true period, is near the peak. So basically, a common mistake in practice, and it's surprisingly often a thing, is that whenever we look into a periodogram like that, and we say, oh, this is the 1% false alarm probability, so the data clearly periodic, then the argument is that implicitly we assume that the truth has to be around that peak, around that periodogram peak. Okay, and the problem here is implicitly this follows from the classical statistical results that we know that say that when you have a so-called argmax estimator, or like an M estimator as we say in statistics, which is in this case is a periodogram peak, is a type of an M estimator. We have all those results that say under some regularity conditions your M estimator is near the truth with some normal probability, some normal distribution with some specific variance. Okay, so it kind of follows from this type of results. But it's easy to see conceptually why this type of test cannot be used for inference. And the argument is very simple, right? Because think about shuffling those periodogram values, right? And I'm going to go back and forth so that I can just illustrate the problems that are here. It's a very important, I think, point here where I want to argue about the problems of the standard methods. So here, suppose that we have, I just go ahead and shuffle all the values for the periodogram, right? The peaks are invariant, right? I'm going to see the same peak. I'm going to get the same peak. So I'm going to get the same test decision. However, by shuffling those periodogram values, I lost all information about the period. Okay, so clearly, logically, this type of tests cannot be used for inference. Okay, because by shuffling, you get the same, you destroy the information for the periods, but the test decision remains the same. Now, the fundamental problem is, I think, fourfold. And the reason is, and the problem lies in the fact that The usual assumptions.
Sorry, Panos, can you
Yeah.
could you elaborate on that? I mean, if you shuffle the periods, I mean, you might find a different. You might, if you move the peak left or right, let's say, you won't destroy the period, right? You're just moving it. So you will change the data set that would represent. But what do you mean by destroying the period?
You'll destroy the information about where the true period is, right? Like you by just shuffling those values, you have no chance of figuring out where the true period is going to lie, right? But what remains invariant is the test decision of whether the data are periodic at all. So
yeah, but then by moving this, you're also changing the data, right? I mean, you're implicitly changing the data, right?
Yeah. So I mean, the argument is that the test for periodicity is distinct from inference about the true period. These two problems are distinct, and you cannot use the periodicity test for doing inference.
You're saying that this decision is ordered, whereas it's based on ordered data, whereas in reality, sorry, I said
the other way around. The decision is based on unordered data,
but it's really in reality it is ordered.
Inference has to be on ordered data. Yes.
Got it. Okay.
Yeah.
Thanks.
Now, specifically, there are 4 problems with this approach, right? Kind of assuming that the true period is near the peak. First of all, and something that's has not been, I think, pointed out enough, is that if we look at that as a likelihood, you can clearly see that this likelihood is not irregular, as we say in statistics, right? It's non-smooth. It's highly non-concave. It is like multimodal. So clearly, in statistics, in order to have good inference, like this type of asymptotic results, we need likelihood to kind of look like this, right? Nice and smooth. Here we don't have that, and that already creates problems for inference, right? These regularity conditions fail. Now, in statistics, we're trained to think mechanically that these conditions hold, but in practice is different. Here's one example where the regularity conditions don't really hold. And the main implication of that is that if you look at the sampling distribution of those periodogram peaks, they can deviate substantially from normal. So assuming that is normal and then pivoting around it to build confidence intervals is going to be quite tricky. Second problem is, yes, Jan.
Are they just the multipliers of each other? Because you can multiply a period by 2 and that's still a period that you detect.
Sorry, I kind of missed you. What is multiplier?
So essentially, for example, if the period you detect is equal to 1.3, then 2.6, 1.2.
Yeah, also the aliasing or harmonics.
Yeah. I think. Yeah, and are these multiple peaks or just corresponding to this type of situation, or it's more?
Yeah, so that's a great question. So in this case, these are harmonics of the main signal. So that's actually the truth here, and the others are harmonics. These are like just integer multiples or like just rational numbers. However, in other examples where we don't have so much power, so this is for 51 Pegasus B. It's a confirmed exoplanet. The signal is pretty strong. For other detections, the signal is not so strong, and actually the observation times have those regularities that we might have a signal that's kind of around 1 day. So we have 1 day type of signals, and then also we have other signals at other days. So there might be mixtures. So it's not always a clear integer. There's not always a clear integer. There's not always like a clear aliasing. Let's say that. Okay. So the second problem is that the observation times are not entirely random, and under this condition, even consistency is not guaranteed. If you look into mathematical statistics, like one condition for consistency is what we call separability of the modes. So let me go back again. Separability means basically that the more data you get, this peak here at the truth, assuming this is the truth, gets more and more distinct from others. So it kind of gets kind of increases, and all the others kind of go down. Now that condition is buried always in the mathematical assumptions, theoretical assumptions, but is usually untestable. And in this case, it's not only untestable, it's actually implausible because we don't have i.i.d. data. Our data have the observations have a very clear sampling bias. They have a very clear patterns in many cases. So not just normality, but even consistency of the periodogram peak is guaranteed here, just because we have an arbitrary, we can have arbitrary observation times. So these two pillars of, let's say, statistical, the standard statistical methods are broken basically. So let me look into the chats. Other false picks. Yes, thanks, Peter. For there's a comment there. A third problem here, not such a big problem, is that the errors are usually assumed i.i.d. normals is to do theory, but it will be nice to be a little more robust to that assumption, right? Kind of assume, and later we're going to make a slightly weaker assumption on that. Finally, something that's underrated, I think, is that there are pernicious effects from hyperparameters. Earlier, I said that here I kind of took a discretization of that period space. Now, if you take this discretization to be higher or lower, then this picture of this periodogram can change drastically. Like if you have worked with this type of data, I'm sure you have encountered this problem. And so the fact that my basic here data can change so much, it makes our inference so fragile, so brittle, that we have to be extra careful. So for all these four reasons, standard methods, I think, break down. Some might say that Bayesian methods can deal with this. I have strong arguments also against that. I think, if anything, the Bayesian methods can make things worse because they hide those identification issues under the rug, right? Because you can impose some priors and can basically bulldoze over those problematic identification areas of the parameter space. So for the sake of time, let me keep going, and we can go back to that philosophical discussion, which I'm sure many statisticians will be happy to have along the way. So let me illustrate first the problems with concrete examples, and then we can move. We can have a kind of quick discussion about those issues, and then I will describe how we propose to deal with those. Here is an example from synthetic data. I'm sampling times. I'm just simulating observation times every day, like every night, with some randomization, with a little bit of randomization around those observation times. Other than that, the model is perfectly periodic. You can see my true period is 1.4, and I have just random normal errors. You can see here that I kind of seeded the data set here so that it's problematic. You see that the observed periodogram peak happens on a distinct mode than the truth. Like this here is the true value 1.4, and the peak happened at a complete, very distinct mode than the truth. That's problem number one. The more important problem, however, is here in this plot. This is because I have access to the model, I can simulate the sampling distribution of my periodogram peak. And here's how this looks like. You can see it's definitely very far from being normal, right? So actually it is discrete. It has these three distinct modes, and then there are also a little bit of support in some other areas. So that's highly problematic. Standard methods cannot deal with this issue. We need a different method to do inference based on this type of sampling distributions. Okay? So that's a very important, I think, problem for inference. So normality clearly does not hold, right? Here is an example from real data, and that's from a paper in 2012 about a potential discovery in Alpha Centauri B. Here, in order to simulate the sampling distribution, I'm just taking the observed the periodogram peak, like what the authors claimed as the estimated period, which was 3.24 days over here. And then I just simulated data based on that using the same observation times. And you can see that I have a peak over here at the observed signal, but there are also some areas here that definitely kind of show that might complicate inference, might be non-trivial, right? And so again, the sampling distribution is not normal. So making those statements of my period is 3.24 plus minus something is really meaningless in these cases, right? Because this plus minus something means that you have a sampling distribution that's normal, and then you pivot from that normal to get these confidence intervals. But when you don't have a sampling distribution that's not normal, in this case, is highly non-normal, it's discrete and is pretty irregular. Those statements of plus minus, statistically, I think are meaningless. So, and here's another example that's also underappreciated, as I said before. This is this plot is for a discretization where I use 10,000 periods. Here's how this plot looks like when you have 2,000 periods. It's completely different. It's the support is in very different places, like around 8 and 10, or even 13 here. and the peaks kind of appear in widely different places compared to before. So you see that I changed the discretization a little bit, which is a hyperparameter really. We don't really think too much about this, but the inference that comes out of this, even if you follow frequentist asymptotic or a Bayesian, will be widely different between those two cases of hyperparameters. So
excuse me,
means
can I have a question?
Yes,
Yeah.
just to conclude, just to say that
Yeah.
all this is saying that the inference can be really sensitive through the standard methods. Yeah, please go ahead. Sorry.
So yeah, I was wondering, how do you construct the sampling distribution of these peaks? Could you
for
tell
the
us?
for the real data?
For this particular case, yeah. How do you do it?
Yeah, for the real data, just assume that the true period is exactly at 3.24 days, which is what was reported by the authors. I estimate all the nuisance parameters, which is the error, the population variance, and the periodic component coefficients. And then from this model, I just start sampling new data and calculating the periodogram and the periodogram peak for each one of these sample data sets.
Okay. Yeah, thank you.
Yep.
Can I ask a question?
Sure.
If you increase the resolution of this histogram, would these bars turn into very narrow, normal-looking bumps?
No, it will. So here, I think this is an example where the sample distribution has stabilized, but the normality, the smoothness does not depend on these values. Actually, if you keep increasing
around 2.24, it wouldn't. That huge bar wouldn't turn into a very narrow peak.
Yeah, it might. If I have more thetas, it might look like this here.
Yeah.
But we might also get things like that. So we're not escaping this problem of like multiple peaks.
Okay, but if you were to construct confidence intervals based on that very narrow peak, presumably you'd get the right answer unless you wanted to have like a huge and a very high confidence level error bar.
Yeah, like it can happen if there's a lot of mass here that you will be able to have a confidence interval around this 3.24 signal. However, if there is a substantial mass in these areas, and by substantial I mean more than 1%, which is not that substantial, right? Then you cannot really make that strong of a claim, right? You have to include those areas as well. And if you follow a standard approach where you do plus minus, you don't get to include those areas, and you're kind of missing, and then you're led to false detections, basically.
Okay, that makes sense. Thanks.
Okay, so this is all to say first that doing the standard method can really break down, right? We don't have the sample distribution that we expect, and also we have this very sensitive dependence on these hyperparameters. So what can we do? Here's our proposal. And I'm going to start with a very simple method, a very simple problem. Suppose that someone tells us, okay, test for me the hypothesis that the true period is equal to that value, and the periodic component coefficients, the regression coefficients are equal to those values. Suppose somehow we have some magical values and we want to test only those. Let's face this very simple task, okay? So what can we do then? If we can solve this simple problem, maybe we have a chance to solve the most difficult problem. So the idea here is the following: like, given this null hypothesis, I immediately can plug in these values into my periodic component, like the sine and cosine terms. So I know exactly what the values are. The values for this component are for the given observation times and under the null, of course. And then I can subtract from the observed data. I can obtain the actual values for the unobserved errors. In the language of randomization inference, we call this a sharp null hypothesis. Like, it's assuming the null, it allows me to impute everything that I haven't observed. In this case, are the periodic components and the errors. So now inference is actually pretty easy, and it's actually pretty easy based on even general assumptions about the errors. I'm not going to get too much into the theory of randomization tests. There's a very nice theory around it. It started with Fisher, but it was formally developed by Lehman and Romano in their textbook, and then by Joe Romano later. And still, there's a lot of ongoing work in randomization methods. For simplicity here, I don't want to get too much into that. For simplicity, let's make an assumption on the errors that my errors are sign symmetric, okay? Which means that for any given observation times, I'm going to assume that the errors if you flip their signs at random, they have the same distribution. That's a pretty weak assumption compared to assuming, let's say, that the errors are independent Gaussian, right? When they're independent Gaussian, they're also sign symmetric. You can change their signs and they're still, their distribution is invariant. But by making this assumption, we're actually allowing the errors to have 5 tails, and we actually are allowing the errors to be heteroscedastic as well. So it's a pretty mild assumption, and we can be even milder than that. So this will be our first major assumption for today. We're just going to assume that the errors in my model, in the radial velocity data, are just sign symmetric, okay? But the actual sign symmetric distribution that they have is completely open. It can be 5 tails, can be something even irregular and even like Cauchy or like something pathological, okay? Still, even with this mild assumption, we can do inference using the framework randomization test. So here's how it works. And excuse my art here is it's pretty lame, but I hope to. I had some math and symbols. I think this will be more readable and hopefully more intuitive. So here's the situation. I have this strong null, this sharp null that I want to test. I have the observation times. I have the data. As I said before, given the null here and the observation times, I can impute all the values for my periodic components because my null is just sharp enough. It tells me what the values are for the parameters. Just plug them in, and I get values for my periodic component. Then I take this periodic component, I subtract from the data, and then now we get the errors as described earlier. Okay. So now what do? Now you try to synthesize data, kind of factual data or like synthetic data, where basically we take those errors and then we just flip their signs at random, plus minus, completely at random, because we just assume that the errors are sign symmetric, right? So this will be fine. And then on top of that, we add the periodic component from before. And this creates new synthetic data, okay? So given this data.
Panos, sorry,
Yeah.
Charlie. Just a quick question. So you're only flipping the sign. So there's only 2 to the whatever the n.
2 to the n, yeah.
2 to the power. You're not doing permutations.
I could do permutations if I assume the errors were exchangeable, but we will need this additional assumption of the errors.
Right. Now I'm just wondering which one is actually more reasonable, because I completely understand your argument that the sign seems a very weak one. But on the other hand, you're assuming that at any particular one, that particular error can go either way.
Yeah.
That could be actually a very strong assumption.
It could be definitely.
Right. Yeah, you're just saying it because usually at the particular location probably can only go one way. It is the permutation on time may actually create this flexibility.
Yeah, but this is one way to avoid having to permute, right? Because permutations require extensibility. And if my errors have some autoregressive structure, it might break, right? It might lead to an invalid test. But assuming this kind of sign symmetry also allows me to have autoregressive error, can accommodate some autoregressive structures as well. So eventually we have to make some assumption, right, about the structure of the errors.
Sure.
Yeah, and
no, not committed. I'm just thinking about which one is actually because right. If you think about autoregressive, that once you have the sign symmetry marginally, to keep the same autoregression is not easy.
It's not easy.
Right.
But there are ways you can do that. I could describe an idea a little bit later. But for now, let's assume that the errors are independent and they have some arbitrary sign symmetric distribution.
One more question.
Yeah.
So is this the way you define this error? Is just the difference between the observed signal and this your hypothesis? So it's not a measurement error in the real data.
It's not the real data, but it is the error that is implied by the null hypothesis. Is the actual errors under the null hypothesis? Yep.
Right. Okay,
yep.
Thanks.
Yep. So now
another
I have
question.
Yeah.
So you're sort of adding and subtracting these epsilons all over to generate this randomized distribution, right?
Yep.
So doesn't that require there to be some large number of data points? I mean, your n should be fairly large, right?
Not really, because even with n to be 20, I have 2 to the 20 different data sets, which is a pretty large number. So even 2 to the 10th is like 1,000. So that's pretty large already. So even with 10, 20, 30 data points, I'm good. I have a very large support potentially.
But when you have small numbers, and it's not so much the number of choices, but the sampling will be very small, won't it? I mean, you get a Coombe-like distribution. I mean, what would make it?
Oh yeah, that's totally fine though. Every combination is valid because I made the assumption that my errors are sign symmetric, right? For any combination of these signs. So any of these data set that I can create under my null hypothesis is a plausible data set.
Okay, and you okay. So you think that having around 10 or 20 is sufficient?
Yeah, completely sufficient. Yeah.
Okay, thanks.
Yeah.
I have another question.
Yeah.
So you're dealing with 2 layers of randomization here. One is the resampling of the periodic part, and the other is the sign flip of the error parts, and then you try to match them. In a more traditional randomization testing procedure or permutation test, we would do the following. We would just use the original y0 NP, and then try to do permutation on the epsilon to match the epsilon with the original YNP. And what do you think this extra layer of randomization that you're doing by flipping the signs using this invariance principle that you assume is adding to the inference? Or would you be aiming for a more conservative type of inference by adding this extra layer of randomness?
Yeah, I don't understand the 2 layers. So the way I see it, there's one layer here where I take these errors and it's completely. This is my only layer of randomization.
Resampling of the y, right?
I'm not doing any resampling of the y's.
So the y is like not changed at all.
Yeah. This is fixed. This y0 is fixed. I completely fixed it because under my null they're fixed.
And their sequence is not changing either.
No. It's completely fixed. Yeah. Yeah.
So you're just every time you're just fitting using a different theta, right? Using it, so that's you're creating the you're gonna so if giving every theta 0, you're gonna do this. Then eventually you're gonna use the kind of the set of theta 0 has not been rejected.
Exactly. You're running ahead, but this will be the idea. Yes.
Right.
Yes. So before we go there, so we have a test statistic, right? And given the observed data, I have an observed value for my test statistic. This set here is the randomized set. So I have a randomization distribution that I built from this synthetic data. I have the observed value here, and now I can can construct the p-value. What's nice about this p-value is that it's exact. So under my null hypothesis, it's an exact p-value. It's not an asymptotic argument. It has the exact correct level for any finite n, which will give me a lot of which basically is going to endow my eventual inference method with finite sample validity, which is very important. So this one here, this p-value, I have to emphasize that it is exact.
Well, it is exact, but you do suffer no, not suffer. I mean, it's maybe the feature, because it's exact, but it's not uniform. It's not even continuous, right? It could be discrete. It is discrete because you only have 2 to the n. The point. So in terms of calibration, might be a little bit of complicated because people. It's like it's not like you can get exactly like 5% test or whatever it is.
Yeah, it's there are ways. So if n is small, then this becomes a problem. If n is 20, 30, 50, let's say, it's not a real problem. It's a problem when the test statistic values are repeated. That can be a problem. That can happen in practice, and then you have to randomize the test decision, which people don't like. But if you introduce a little bit of random test decisions, then you can get to the 5% level. But in practice, it's not really an issue, like for more moderately large n. Okay, so this is a p-value now, and you might say, okay, now we're testing for theta 0, size 0, but what if, in practice, what we want to test is only the period, right? So how can we do it? Well, the easy solution is, and the conservative solution is to test that by taking the soup over all those p-values, okay? So you're testing many different values for this nuisance parameters. You take the soup over it, and then you reject based on that p-value. I'll get back to that. This can be computationally demanding, but I'll get back to that. Suppose there's a way to do this, then as Shaoli suggested, we can invert that test to build now a confidence set. And this is our first method that we propose for inference on the unknown periodicity. So what does this test inversion means? Basically, it says, well, take all the possible parameter values and then make this test for every parameter value, like period value, that's a candidate period value. And then you're going to retain all those that are not rejected by your test. And this is now your confidence set. And I should emphasize the idea of the confidence set because it's quite distinct from the confidence interval, okay? Now, a confidence set here has the same property as confidence intervals in the sense that it does cover our true parameter with the specified coverage probability. Okay, we can construct it in a way such that, let's say, this confidence set that I can create contains my true parameter 99% of the times, 99% probability. But it's a different idea from confidence intervals. As I mentioned earlier, confidence intervals require you to have a normal sample distribution, which in this case it fails, right? But a confidence set is a more general idea. Like if the sample distribution is indeed looks like a normal, then the confidence set is going to look very similar to the confidence interval. But if the actual distribution is very different from normal, it's kind of has mixture, is irregular, then the confidence set is going to be quite different than the confidence interval, but it's going to be valid. Whereas the confidence interval might be either invalid or might be too imprecise, like might be too wide, right? Because you have to take into account all this variations spread in the sample distribution. So in other terms, if things work well, behave well, then this confidence set is going to look very similar to the confidence interval that standard methods give you. If not, then the confidence set will remain valid, right? Because it takes this irregularity into account. So I think as an idea of inference, as a tool, as a device, is more appropriate in this type of problems than what the standard methods give you.
Sorry,
and now,
can I interrupt for a moment? So I'm not quite sure I understand how this will avoid the problem of harmonics and the aliasing and all those other nice things that affect Lobscargo.
Well, it might depends what we mean though by avoid, right? It might happen that in our confidence set we might have two very different periods, okay? But that's something it's a feature of the problem. So when the confidence set contains different periods, it means that neither of these two periods can be rejected, right? So and so the statistics are telling you that, you know, from a frequency perspective, both of them are compatible with the data. I know that there's a tendency practice to say, okay, I want to find the one signal and then kind of remove the aliasing, right? Remove all the other nuisance signals. But I think we have to resist that temptation and really let the data speak and say, look, what periods here are compatible with the data? And if they are, we find two harmonics here that are, you know, they have like an integer relationship, both of them should be in the confidence set because both of them could be the true period. I'm going to describe some examples very soon where this problem will show up and it will not show up. So it will help, I guess, kind of ground those ideas even more. Okay. So that's a great question. I think it's very practical too. Now, you might say this is too much, so I have to maximize over this parameter space. It's definitely doable because this set is convex, but I haven't attempted to do that. Now, one way to approximate that is to essentially plug in a restricted MLE. Like for any null hypothesis for the period, just estimate those regression coefficients, then plug them into your p-value and kind of follow the same idea. And then your coverage is asymptotically correct, is asymptotically valid. Now, this number is quite small, depending on how fast your estimator is for this for the nuisance parameters. Okay. Now, if you want to save computation time, then you can do that approximation as well.
Panos, Panos, are you? But in practice, when you actually do this, you do actually set a grid value of the null value, right? And do this rejection.
You mean for the periods?
Right. I mean, because you need to test each one, then to collect those you're not rejecting, right?
Yeah.
But you're doing this, obviously you cannot do continuously, so you'll be doing some discretizations. Are you doing something clever than just equal spaced. There's some other schemes there to both for speeding up the computation as well as to. I think the one advantage of your method is saying that a value near another one already accepted, not necessarily will have a stronger evidence to be accepted compared to some values far away, right? There's no utility distance, that's sort of that continuity. So do you build that into your way of computing that to actually get these plausible values?
That's an excellent point. For the first component of your question, for this theta, I don't do something smart to begin with, in the sense that there has been some useful discussions of how you really choose that theta. Usually they say take a uniform discretization, like a regular discretization in the log space of the period So this is basically what I'm doing. So I'm taking a uniform spacing on the log space, but then I'm doing some computational tricks to speed this up. One is that I'm doing these calculations. I'm sending these calculations to different nodes, like in a supercomputing cluster, because all of these tests are completely independent from one another. So you can test this completely independently. Like computer scientists say that it's embarrassingly parallelizable. So you can make these tests completely dependent from one another. So that's one. And the second thing is that I'm doing this test only for the major peaks in my periodogram, like the ones that exceed, let's say, 10% or 20% of the highest peak. That's a heuristic, but it's sufficient to discover and identifiability issues, at least for the applications that I'm considering. Now, depending on how much computation you have, you can change that, but I'm not testing all the possible thetas, but I'm testing the ones that correspond to the the highest peaks, let's say the 50 or the 100 highest peaks. So, and as I said, that's usually enough to detect issues. But
no, I think computation, that's fine, but theoretically
no.
That alters your coverage property.
Yes.
It can become a conditional one, right?
It does, definitely. Yeah, it's only a computational trick. Yeah. So here's the overall the method that I propose. Choose a grid theta, choose your test statistic. You have the data. Then for every value in the possible period, then just do this randomization test and then include it into your confidence set if that p-value does not reject it, right? And this is in the end what we return, this confidence set. So why is it worth doing this? Well, let me enumerate the advantages and then I can describe a little bit the challenges. And some of you have already mentioned those have made these excellent points already. First of all, this confidence set, like in the full implementation, is valid in finite samples. That's finite sample validity. So I don't have to wait for asymptotics to kick in or anything. I don't need anything like that. So my method is going to work, is going to be valid for any small n, right, in its full implementation. We make no assumption about the test statistic, and that's actually quite important. I didn't assume that the test statistic is normal. I didn't assume it's even consistent. So you can do inference even with inconsistent estimators, right? This is following that kind of approach. Third, we make no assumption about the observation design or the spacings. Our method works seamlessly with equal or unequal observations. So that's also a thing important because our method conditions on the observation times. And finally, the inference is conditional on those hyperparameters, like the discretization of my parameter space, the period space. And any irregularities that fall from this type of hyperparameters, we're going to condition on those. And in some sense, we control for those as well. Right? So we don't have to rely on those hyperparameters, like a careful, let's say, tuning of those. Now, some challenges, of course. First of all, is the method conservative? In theory, it is. And it's hard to do also theory to understand how much conservative it is. So we can, my own proposal is to really kind of look empirically, try to validate it empirically, kind of calibrate it empirically on that matter. I will very soon describe how I would do this in practice. So this is coming up. Now, the choice of test statistic can be critical.
Quick question.
Yeah.
So when you say conservative, you mean low power, right? I mean,
yeah, meaning that the confidence set might include many different periods, right? Of course, if I report to you,
okay,
yeah.
Okay.
So I could tell you, here's a confidence set. That's theta. It's all your possible periods. That of course is going to cover the true period, but it's not informative, right? It's not sharp. It's just a very weak inference. Yes. So we want the theta to be as narrow as possible, of course. And now the choice of the test statistic, as I said earlier, we make no assumption about the test statistic, but of course this freedom can be a curse because now you have to decide what test statistic makes sense here. It's not really so hard. It's not really so challenging because you can use the classical test statistic that even the Fisher test statistic actually can give you quite sharp inference. We use a different kind of test statistic, which is we take the periodogram peak minus the periodogram value at the null. In general, it would be nice to have some theory here, but we don't have that. Like what kind of test statistic we should use?
So Panos, can I do something? Why can't I just run all test statistics I can think of, and I got all kinds of sets, and I do intersection of these sets and play with the probability to get the the confidence. If something keeps showing up by any test, will there be some way of getting sharper inference?
Well, if you take the union, it's a valid method, but if you take the intersection, then you have to understand the joint distribution of those test statistics in order to be able to make the claims, right? So it's
right, but I can do some kind of Bonferroni correction or something of that nature.
Yeah, that will be fine. Yes.
Yeah, okay.
Yeah, that will be completely fine. Yeah. But we'd like to have some guidance here. But in general, the idea is that if you have a good just plug in the best estimator for the period that you have, and that will be the most reasonable approach here. And finally, as I said earlier, and many of you have pointed out, what we're doing here is we're exchanging this nice finite sample properties with more computation, with actually a lot of computation, right? Because we have to do that for every candidate value in our period space. And we have to parallelize if you want to be like 100% kind of covered by this method. So it is computationally intensive, but I think we're able in our case to do everything within a couple of hours in all of our 4 exoplanet detections with many samples in a couple of hours using a 400 node supercomputing cluster. So we'd like to speed this up a little more, but I think it's a small price to pay if we want really to avoid these false detections, right? And I think our method is more suited to avoid these false detections than the more standard methods. But there's still work to be done here for the computation, of course. Okay, so what does our method produce? Just let me give you the practical aspect of it, right? And so that we can kind of appreciate those advantages. So let me go back to the synthetic data example. Our main product is basically this: is we get a table that looks like this, which is this includes our confidence sets here, the 95% and the 99%. What you see here on the left is just some candidate values for my period, and here are this yes or no is whether that period is included in the confidence set or not. You can see here in this example that I have a bunch of different periods that are included. And one nice product of our method here is that you can immediately see just by looking at these accepted periods that there are identifiability issues here immediately, right? You can see that 0.5, 0.7, 1.4, 3.4, all of them are consistent like with the observed data. So, and a nice thing here is also that we're not tricked by this peak over here because the truth is included in that confidence set. So that's a kind of it's a nice feature of our application here. But of course, let's look into the real examples because this is where the real action happens, and I think hopefully we're going to appreciate those benefits a little more. Now, before I go to the real applications, yes, I'm open to.
One more question here. So you've got these p-values.
Mm-hmm.
Are you doing anything with this p-value? Any decision on this yes or no periods?
Yeah. So it's a simple comparison for the 95% confidence set. I just check to see whether this p-value exceeds 0.05 or not. For the 99% confidence set, I'm just looking to see whether this p-value exceeds 0.01. It's a simple comparison, yeah. And I don't have to make any correction because this corresponds to distinct null hypothesis.
Okay. All right. Okay.
Yeah,
okay.
I have another comment on the computation side, because 2 or 3 years ago, my student and I took a crack at a similar problem, and we were looking working on top of the LS method also. The way that we treat this this problem of having to do grid points on a space of theta is that we do it in a greedy way. Because if you think about the issue, if you think about the fact that when you only consider one period, the space for the period detection becomes more continuous, in the sense that you could underestimate the theta for a little bit, but still the alignment of the estimated curve versus the observed curve is still pretty good. So we use that property to incur some kind of continuous property of the estimation of this theta parameter, and then try to find the largest multiplier of the desired period in my time series first, and then try to do the search for divisors of this particular largest possible period in my time series. And in there, you could, for the largest one, you could use Gaussian process type of optimizations because of the continuity property you have locally when you consider a smaller number of periods in your time series.
Yeah, that's interesting. I really didn't look too much into the computational tricks that are possible to speed things up. My method is really just to take this periodogram, slice it on some level, and then take only those peaks on that exceed that level. And you can reduce it. You can be, if you want to be conservative, you can reduce that. If you want to be a little more ambitious, you can increase it. But I haven't done much more than that. So I think what you described is definitely makes sense to speed these calculations up, because there are many. I think what you're saying is you can just kind of lump some peaks together based on their relationship and things like that. You can definitely speed this up. Yeah, I didn't do this kind of sophisticated things. I only did this simple kind of slicing, let's say. Okay, so let me move now to the applications. This has pictures and results, so this hopefully will be easier to digest. So here's the 51peg SAB. That's a confirmed exoplanets iconic, let's say, detection. Here's the periodogram, and on the right I have the observed the coordinate set that we calculate. And you can see here that there's only one value, 4.23 days. 4.23 days that is accepted in our confidence sets, like the 95% and the 99%, which indicates that there's a very clear signal here. There are no identification issues. Our method is very kind of can kind of sharply identify that underlying period. And this also goes to Vinay's question that you can see those peaks, right? That you might be worried about, like these seem to be harmonics. What am I going to do about it? We're doing nothing really about it. We're considering all of this as being, we are testing the hypothesis that this could be the real signal, but it's just rejected from the test. So here the data are just, there's a very strong signal such that we can basically reject those as a true signal. It's only this one that stands up to scrutiny. So this is a case where even though I have this very distinct aliasing problem, I'm able to identify that signal exactly correctly. Okay. Here's another example from GLISA 4036b. That's also confirmed exoplanet. Same deal here. Even though I have a periodogram that has a little more noise, a little less power, we're able to sharply identify that signal as well as 2.64 days. No identification issues here. We have a clean identification. Now, these two examples are what I mentioned earlier, can serve as examples to validate our method in the sense that our method is not too conservative, right? If the method was conservative, then for this confirmed exoplanets, we would probably get like a larger confidence sets. Now, the fact that we don't get large confidence sets and our confidence set has only one period value indicates that the signal is very strong, and there's probably our method is not too conservative, or at least shouldn't be empirically that much of a concern. Now, that's empirically, of course, I don't have any theoretical backing to that.
But Panos, I have to ask you then, even this is empirical, how many examples you have to go through to find these two?
Oh, actually, I didn't go. These are I was just asked. We kind of follow the double-blind procedure where Jacob will send me examples, and I will just fit the method, and then I will just get him the results. So this is I only tried 2 confirmed exoplanets. These are these are the results that we got.
That's very impressive. Yeah.
So if there are other examples, we'll be happy to consider those too. I'm just as I said, this is ongoing, completely open to test that. But the fact that we see those, I mean, it could be just again a caveat. it could be that we see that the power is very high, right? These numbers kind of 0.7 or like 0.8. These are pretty high power values, pretty high likelihood values. So in reality, the values that we get are, so here it means that the signal is like very strong. So maybe it could be that our method is not conservative when the signal is too strong, maybe. But that's completely open. Like we'd like to see more examples and perhaps test it in more examples.
But what you like to expect. You like method say.
You'd like, yes.
Yeah, if it's a strong signal, then you know it should have, any method should have picked up, right? Any method of any good should have picked up, right?
Definitely,
right.
Yeah, definitely. Yeah. That's why I view this as a nice validation of what we're doing, at least. Here's another example of an unconfirmed exoplanet. And this is from Alpha Centauri b. There was a Nature paper in 2012. And here the situation is completely different. We don't have, there's severe identification issues. You can see that our 99% interval contains all those different periods, right? You can see that 0.7 is consistent with 0.7 days consistent with the data. 0.8 is, 1 day is, 2, 3, up to 61 day signals. All of them are consistent with the data. What's additionally concerning here is that we have signals that are near the 1 day periodicities, right? Which is the kind of traditionally connected to the nightly observation cycles. So here's an example where we just cannot confirm that this detection, right? There is definitely evidence that more evidence is needed. We don't refute it per se, but there's definitely the evidence is very weak here. Okay?
But on the other hand, for this one, I mean, the 95% one actually, now it's interesting, right? Because if the percentage high, you would include it because it tried to do.
Interesting. Yeah.
So how do you think about the 95% one? You know, it does seem to much sharper, although you still have the 2.
Yeah.
Yeah.
So Charles is referring to this 95 that has only two values. Like it really depends now. I think that's a broader statistical question, right, Charlie? It's like what level is really the appropriate level here? I myself, I think for scientific discovery, we should put those levels to be pretty small. Like, so I will definitely trust more than 99%. This is my default, at least in the paper, this is the default level that we're using, but I think that's open for more like general discussion, really, what's the appropriate level.
I would ask Vinay and Anita, you know, what they think, because I know sometimes they even use 50% confidence interval, right? So,
no,
not for this. I understand that, but would you feel comfortable the 95 one saying that's more suggestive? Because the other one, you know, 99 is
well, you know, that's the question also about your priors, and here you didn't have any prior assumptions, right? So I think in the decision and you know, final assignment or whether or not to trust this 95%, there will be some physical understanding of the process, and you may accept 95% or not, right? 0.95. So that's my opinion. I don't know, Vinay, what do you think?
I mean, I think the priors are important. I mean, Alpha Cent B, when it was first reported, was really a wow result, and I don't think it has held up all that well. So
I'm going to make a note. I'm going to make a remark about that. So.
Go ahead. Yeah.
Oh yeah, I was about to say that there have been some objections to it, and I think there's a paper by Ratzpaul et al. Like 2015, 2016, where they actually follow the same approach as Stigler and Wagner that they did for the biological extinction data, where they simulate observations, they keep the same observation times, and they try to see whether that peak exists in the periodograms. And what they find is that in all of their simulations, that 3.24 peak, it kind of appears in all of the simulations as a local peak, not as a global peak. So they kind of use this as in some other simulations as an argument that, you know, there's probably there's kind of likely a problem here. There's probably a ghost in this time series. But as what do we bring to the table here? I think is that we actually have a principles. We do agree with this result, but we do also have a principal statistical method behind it, right? This year, the method that have been developed to check those whether these are true or false discoveries are mainly heuristics, and that paper is also kind of is applying those heuristics. And I would argue against using those heuristics, because actually even in the original paper they did use a similar heuristic where they took out the signal and then they kind of resampled the data, and it kind of in this heuristic it held up, the discovery held up. So it's unclear what these heuristics are testing. It's unclear what is the expected behavior of these heuristics under the null and under the alternative. So statistically speaking, they're not as sound. They're useful, but this shouldn't be the last thing that we try. I think that more reasonable, I think more principled approach will be to kind of follow simulation, like a randomization setup, as similar to what we have over here. But yeah, it's not, I don't, and my collaborator tells me that this is not a discovery that's believed overall by experts. But I think it's nice to have a kind of statistical, concrete statistical evidence that this is not like a sharp discovery.
Yeah, I think that is a good way of saying that it's not a sharp discovery.
Yeah, yeah. Okay, here's another example that has also, I think, created a lot of buzz and excitement. This is the Escude et al. This 2016 in Proxima Centauri. Here, the situation is better than before. For the 99% interval, you see there is a signal at 0.9164 days and one at 11.17 days. The p-value for this nuisance signal is kind of small, it's 1.7%. So it's kind of near the 1% threshold. But technically speaking, I hate to be, like that pedantic, but technically speaking, it cannot be rejected, right, at the 1% level. So we have these two signals here. And now, my collaborator thinks this discovery is robust. I do think is also willing to concur that it's robust. But if we really want to be cautious here, there's a little, there's a little more evidence that's needed to just finally kind of confirm that discovery as well. So, and there's not to be too negative. The next few slides, and these will be the last slides, I do talk about how we can really randomize a little bit our observations so that we were able to remove those, kind of exclude those, reject those nuisance signals and identify those candidate signals. So yeah, so to summarize, for the confirmed exoplanets, we do have sharp identification. For the unconfirmed, the situation is strange, right? For one, we don't have, there's severe problems. For this one, mostly robust, but there's this a tiny nuisance signal there that perhaps needs to be addressed. Okay, any questions about these applications? That's good. Okay, so yeah, so in order to be constructive, I have a couple of final slides about what can we do in practice to avoid these identification issues, right? And our method is pretty straightforward, which is basically invert our method to say, okay, how can I design this observation times such that my confidence set is sharp? That's basically what we ask. It's a basic simulation study, right? So suppose you have a candidate signal. Suppose in this Escude et al. Study, you want to confirm really that the signal is real at 11 days. So what do? Just assume that this is a true signal and then ask the question, how much randomness do I need, or how many more observations do I need so that my confidence set includes only those values, like around the 11 days. That's basically it. It's just a simple simulation study. There's nothing like theoretical here. And we did that for all of these 4 applications, this type of simulation study. For the confirmed exoplanets, we don't need any additional randomization. We don't need any additional observations, and things are nice. For Alpha Centauri B, this result tells me that I need plus minus 4 hours of randomization. If I wanted, this number is telling me that with the same sample size, you needed a plus minus 4 randomization in your original observation time. That's an 8-hour window, completely unrealistic because obviously it interferes between nightly and daily observations. So there's another way to describe those identification issues. Now,
plus minus 8 hours essentially means you move from Australia to South Africa.
Yeah, exactly. Yeah. So it's maybe it's doable, but it seems like experts tell me it's a large number. It's a large randomization to ask. Or if you can allow for a little bit of randomization in your observation times, you just need 137 new observations. It's a pretty large number compared to the original sample size, which is 190 or something like that. So this is telling you that if the 3.24 signal is real, then you need that additional number of observations to identify that signal. The numbers for Proxima Centauri are much better. You need a plus like a 3-hour window of randomization, or you need an additional 17 new observations. And if you want to increase a little bit the randomization, this number could be 15 or even 10. So you was very close to discovery. So if that 11-day signal is real, we just need a couple of more observations, and then we're good to go. And I think this is very useful in practice because, this will be our next goal actually, because my collaborator has built this new new instrument, and would like to test those new observation designs where in the first stage, we just collect some data, we found some nuisance signals, and then we ask the question, okay, how many more samples do I need to get rid of those signals? Or like, how much should I randomize those observation times to get rid of those signals? So I kind of try to answer questions like that and guide the observation times in such a manner, which I think it will be useful in practice. And it really is not very different from the type of sample size calculations we do in experiments or like clinical trials. So we try to bring that mindset in astronomy as well, which I think will help with kind of connect the statistical aspect, the inference, with the observations, like the mechanical aspect, let's say. So yeah, that's basically it. So I'm happy to take questions about this or other things, but I don't have a conclusion. I don't want to take any more time. As I said, there's a working paper. There's another paper from last year that talks about COVID. It basically retrofitted that method in a simpler setting where the conditions are even more mild and plausible. We don't have nuisance parameters, and I'm happy to talk about that as well. But roughly, this is the idea, right? Kind of do inference not based on asymptotics, on kind of good expected behavior, but based on really what the sample distribution looks like. So yeah, thanks for your attention. Again, thanks for the invite and the excellent questions.
Thank you. Very nice. So, I mean, so you thought that you were going to finish this in 40 minutes, didn't you?
I thought so, yeah.
we have been pretty gentle with him today, but not anymore. Now we can ask all sorts of questions.
Yes.
So this is really very nice, and I can also see this can be it's easier for people to understand. I think people can try those things. Okay, so now let's push a little bit harder. The fundamental issue here, not issue, I mean, the thing has become, the randomization inference is always so nice because you entirely have control what the distribution is. It's all created by your randomization. Now, the key thing here, which is kind of tricky, because by flipping each one, plus minus, I do agree that's at least marginally, that seems the kind of weakest assumption to assume to ensure the mean is zero, right? Just plus minus. But then the problem is, like, you do need to worry a little bit about the correlation between these flipping, right? Because currently you're doing entirely independent of each other. That allows you to do all this stuff. So is it possible the next step is to, let's say, do a Markov chain, right? Because you have a sequence, like, allowing some kind of dependence. I mean, it's still binary, marginally still, flipping coin, the sign, but you can induce some correlations. If the previous one is plus, this one is more likely going to be plus than a minus, because the thing, I need to think through whether this actually is a good thing or bad thing. The thing is, like, when the model is not fitting, let's say you use a theta, which is clearly not right, so you will have these very large residuals, right? Okay, but the very large residual, what's happening here is that you allow the next residual just next to it, it could be entirely flipped the other way around, right? Let's say residual is very big. Then you have these right. There's really big residuals, and you can see how that will create a very strong, signal, not signal, what do you call the residual errors, because to reject your null. But it's not entirely clear to me that it is a randomization. It's obviously valid and your assumption, but whether that it really give us the kind of a confidence we need for the real problem, right? Because the real problem, the arrows may not be able to flip that quickly with that's large sign. Large the other direction. Right? So that's
this is completely valid. Here's my thought, and we do have a quick remark about this in the paper. So suppose, let's say that in many cases people might say, okay, let me impose a Gaussian process on this, right? On these errors. So suppose this sigma. What you could do is first decorrelate the errors, right? And then correlate it again, right? Or like something like that. Where so first you decorrelate, then you do this plus minus on the decorrelated errors, and then you correlate back with the correct correlation structure.
Sure, you could do that.
And then in practice, you could try to estimate that using a Gaussian process model. So there's nothing wrong with doing something like that. Of course, then it becomes approximate again. Then you need a little bit of theory, but we can accommodate potentially this type of structures. I would leave this for future work, I guess. but it's would definitely have some freedom there in choosing those structures. Like other things will be, in many cases the observations come in like different years, like different months, right? In this case, you might have residuals here and here and here, and you might do a type of a wild bootstrap type of thing, like where you do the cluster. You assume that these things are independent, so you can do this science across
within each, right.
Yeah, and then you kind of leave the intra-cluster dependence unchanged. So you
I
also
see.
have that freedom
see.
as well.
I
And I
see.
think the benefit here is really that you're always fine testing you can still test the method with all these different correlation structures, right? Like if your inference does not change, that's great, because we are robust to this assumption on the errors. If the inference changes, then we can just report it, right? Our inference is sensitive to this correlation structure, so it's really important to nail that down before we go back to that method and do inference. So I think it can be actually quite useful. We can really use it to our advantage and use it as a sensitivity analysis tool, right? Which is not really thought in.
Right. No,
so,
actually reminds me in terms of creating these correlations to make it more general. This sounds like you may have already have talked to her. You probably should talk to Rena, because this whole literature on knockoff, right? They essentially is creating these faked version, keeping all the conditional dependence, and I mean it's essentially, I think that technique should use it for this residual process. Right, and then
that's interesting. The knockoff,
right, and they have done quite a bit. And thinking further, I'm just thinking more about randomization, and I know you're also interested in fiduciary inference. It's actually really getting very close to be, because this is the thing I need to think this through, right? Because you essentially is saying that you have a distribution, you have a randomized distribution about the errors, and you essentially want to keep that structure. And using these equations essentially as a really the fiduciary constraint, right? And then and say, what is that? If I continuously to believe these epsilons, what values of zetas can be eliminated?
Yes,
right?
exactly.
But for whatever cannot be eliminated, I just keep them.
But this is why we talked about fiducial a while ago, right? I'm still trying to understand where this thing fits. I think the fiducial, I think it takes it one step further and assumes that theta has a distribution, that theta star has right, like the parameter has, and you're using this randomization distribution, you will use it as a distribution for your parameters. I think.
You don't need to assume theta as a distribution. The distribution of theta is induced by the distribution of epsilon. Right?
Yes,
because for every given epsilon, you solve the equation.
Yeah.
And whatever the epsilon, the theta coming, if you keep doing the epsilon, and then you solve it. So that's very similar. I mean, because you're doing, except that you only allow this discrete number of possible epsilon here. And for each one of them, you essentially, you could also do the other way around, which is the instead of that's another way of actually doing it. But you need to know the distribution of the epsilon. Instead of you're doing this hypothesis testing to reject it, not rejecting it, you could just put in whatever epsilon value into this equation, solve for the theta, right? And if you keep doing that, you will get sets of value of actually get a distribution of theta as well. I wonder if these two things actually, there gotta be some ways of relate to each other.
Yeah, but fiducial doesn't do the testing version, does it?
No, fiduciary do the other way around, right? Because here's you're giving theta and trying to get the epsilon permuted.
Yes.
Theirs is you giving epsilon, you solve it for theta.
You back out theta.
But I wonder whether this is because there's a duality somewhere.
It's interesting. Yeah.
Right.
A quick question about the this whole business of the epsilons. So this obviously won't work for Poisson.
Why not?
But I was wondering.
Why not?
It wouldn't be symmetric, right? It won't be sign symmetric.
So you want to assume that the errors are Poisson?
Yeah.
If they're independent, then we can assume that these errors are exchangeable. So instead of just changing their signs, you just permute them.
No, but then that would, you would have the case where the intensities vary, right? So so it would be heteroscedastic, it wouldn't. it won't be
Yeah, if
constant.
they're if they're heteroscedastic, you cannot. Yeah, you will be able to do that.
But I was wondering though if it's possible to just, the what you're doing with the sign flipping is essentially assuming that whatever the yp and the y obs, they're flippable, right? So in principle you could make the same correction assume for a Poisson distribution, right? I mean, if you have a predicted y, you calculate the Poisson likelihood at y obs and vice versa.
Well, if the Poisson, would that be even easier? Because you certainly you do not write an additive model, right? Because for the Poisson, if you assume it's a Poisson, you're putting epsilon, and because if you get the intensity, then you know how to draw the error, because it's a Poisson. Once you have the intensity, you know how to draw you know how to draw the error, right? The only thing is the intensity itself is not fully specified, so you do have to estimate it. There's a nuisance parameter, right? That may actually destroys a little bit of the being exact. But if you have a fully specified intensity, then the permutation, the idea here will be even simpler, right? You just draw the data from the Poisson, you just fit it. Now, but of course, you still need to look at the residual. You can still look at that. Not like a chi-square fitting. You still can look at the residual, that kind of a test statistics, right?
But Vinay, at some point I looked into, is it Feldman and Cousins?
Cousins, yeah.
At some point I looked into that problem, and actually you can use this method for that problem as well to get exact converse intervals. So maybe you're kind of referring, because I think in that case we also have to deal with Poisson models. So maybe we can discuss that a little bit more, because I was interested in just discussing that with someone. Yeah, Feldman and Cousins. Yeah, and I have a procedure.
Well, actually, the Brett Horst. He was the one who first did this Fourier fitting in the Poisson case. So maybe.
Oh, okay, yeah. I'd be happy to look into like actual examples. And it sounds like, as Shaoli said, if this is fully parametric, we actually know the distribution as well, the Poisson. Then it might be easier in the sense that I might be able to sample directly from the model, instead of assuming these sign symmetries, because here we're just not assuming anything about the errors, right? But it also depends on the actual model, like the details.
Okay, we have run out of time. However, if there are any quick questions, I suppose now is the time to ask. If not, let's thank you, Panos, once more.
Thank you so much.
Very, very nice.
Just a very brief
Casey, go
ahead. Your
ahead.
working paper available on your website?
Yes, it is. I can share the link just now.
Yeah, please. Would be nice.
And of course, it's the time where my website decides to be slow. All right, I think I copied the
into the chat.
Can you just give it to Vinay to put on the webpage?
Yeah, actually, yeah. You can send it to me and I will put it on the webpage.
Yeah, that's the best.
There it is. Oops. Yeah. Okay. I'll send it. Yeah. Sorry. It's just it's slow now. I'll send it to you, Vinay, and then you can share it.
Sure.
Thank you.
All right. Okay. Any other comments, questions? And if not, thank you all for joining. I think we're not scheduled for anything else until April, late April, but you never know. Keep an eye on your emails.
Exactly, that's what happens. We just
will have more.
Right. We get message from Shaoli saying 2 days from now we have to have a talk, and it's nice. But it's nice. It was very good, very interesting.
No, this was very useful.
Yeah, so this seems like a very practical, and I think it's true. The randomization. It is computational very intensive. That's the old days that people avoided, but it is a very interesting way of thinking about it, and so it's great.